Hello everyone, so today we are going to solve another interesting problem number 410, split array largest sum. And the problem says we have been given an integer array nums and integer k, split nums into k non-empty subarrays such that the largest number of any subarray is minimized. And they want us to return the minimized largest sum of the split. Okay, so we have been given this array, and which is like this. We have 7 2 5 10 8, and we have to split it into two ways such that the number of such that the largest sum among the two subarrays is only 80 is the largest. So how I'm going to approach this problem is, first I'm going to see how many subarrays I can split from the original array. So the first would be if I create all the original numbers, split the original numbers in the subarrays. So this would be, and here the sum of all the subarrays would be the individual number. The second option that I have is I can take two numbers at a time and then split the subarrays. Here the sum that I'm getting for the subarrays, I'm noting it down. So here the sum is 9, here the sum is 15, and here the sum is 8. Now I want to check, can I make better option if I split in 3. So if I do 7 to 5 and then 10 and 18, 10 and 8, then I get the sum as 7 2, which is 7 plus 2 plus 9, so which is 14, and here it is 18. So this is the largest sum. And there is one more another way that I can split, it would be like if I do 7 and 2, and here I would do 5, 10 and 8, then the sum that I'm getting is, here I'm getting 9, and here I'm getting 8 plus 5 is 13 plus 10 is 23. Now the question is, why do I want to choose this over this one? So here in the problem it is said that we want the largest sum to be minimized of the split. So here the difference is so much. So here the difference between these two sum is 23 minus 9 is 14, and but here the difference between the two subarrays is just 4, and this is what we want. So one thing I noticed, that if I decrease the number of subarrays, so then when the number of subarrays are decreasing, so initially we had 5 subarrays over here, then we had 3 subarrays, now we have 2 subarrays, and then we have 2 subarrays more. So I think one thing I observed, that as the number of subarrays are decreasing, my subarray sum, that is increasing. So I can make one observation, that the number of subarray is inversely proportional to the sum of the subarray that we have. And using this property, we can apply binary search into a search range. So the minimum sum that we can obtain from the original array that we have would be 10, and the maximum subarray the maximum sum that we can get from the original array would be summation of the nums, and that would be 32. Now in this 10 to 32, we know that this function is decreasing. So what we can do is we can apply the binary search method, because we can see that this function is monotonically decreasing, and we will place two pointers, one at the right and one at the left, and we'll find the number where we have the minimum where we have the split and the minimized largest sum. So here we have L and R, and now we are starting from this, and then we are looking for this number K, where our answer is lying in this search region. So this is the value that we are looking for, and we'll be using the binary search method uh, to reach to this region by splitting the region into two halves every time and moving our left and right pointers. So we see that if the function value is the mid value that we are going to calculate, so the mid would be L plus R by 2, and as if it is greater than the split K count that we are seeing, so for the first case it would be 10 plus 32 by 2, that would be 21. So 21 is more than the so this function will give me a count that we can will with which we'll check that what is the number of subarrays that we can get with this sum, that with the maximum sum of 21. So if the sum is maximum, if the sum is, if we keep the sum 21, then we can split the subarrays like this. So a maximum of 7, 2 and 5 we can obtain. And similarly, the next number that we, if we add 10 into this, then this number becomes more than 20, this number becomes more than 21 of the sum. So we'll split it over here, and with this split we'll generate the count value, and with this count value we'll check if this count is more than the K, then we are sure that we need to update our left pointer towards the mid. So what we'll do is we'll update this left towards the mid in this case. This left will be updated toward the mid, and similarly, so here what we'll do is we'll update this left toward the mid, and otherwise we'll update our, so if the mid is value returned after the mid is less than K, then we'll update our right toward the mid, and in the end we both will convert, this L and R will converge and to add one value of answer that we are in which we are, and we'll return this L as the maximum split. So with me writing the code, I think that would be more clear. And there would be one more thing, that we need to define this function that we are going to use. So this function would be f of mid. So what we'll do is this, in this function, that this function we want to get the count of the subarrays which has this maximum sum, I would say. So that will use the general greedy approach, that as we are traversing the original array nums, we'll grab all the values and we'll check if the sum is more than the maximum sum that we have obtained, and if it is, then we'll increment our count by 1, and in the end we'll return this count value. So once I write the code, it would be much more clear to you. And so now let's go into the coding part and see, and I'm going to show you how I'm developing the code as I'm thinking along. So we have these two pointers, left and right. So left is initialized at the maximum of the nums value, and right is initialized as the total value of the sum. And we'll do the general binary search, while left is less than right. We'll calculate the mid is L plus R by 2, and then we'll just check with our function, if this function gives the value greater than K, then we'll update our left towards the mid, otherwise we'll just update our right with toward the mid, and in the end we'll return the L. And now we need to write this function that we are going to define, and this is the maximum sum that we are having at any given point of time. So that would be, so we need two variables, one for sum and one for count. So we initialize the sum as infinity and count at 0, and we'll traverse the whole nums array, and for every number we're going to add this number into our sum, and with this sum we'll check if this sum has reached to the maximum sum that we have obtained by dividing the region into two halves. And if it is greater, then we'll start the next subarray with this sum, and we'll increment the count as well by 1, and in the end we are looking for this count value only, and that one will return. Now let's run our code and see how it performs. So it has been accepted for first test case, and now let's run it for all the examples test cases and see how it performs for all the test cases. So now let's submit our code. It has been accepted and it's really fast. So that's the approach for solving this problem, and the time complexity for this uh, solution is O of n for the binary search. And since we are also doing this, we are also using one for loop inside the inside the function count function that we have declared. So that would be O of n. So in total these both are getting multiplied over here, since this function is inside the binary search. So we are, the total time complexity that would be of O of n log m, where m is the sum of all the elements in the array, and we are not using any space, so space complexity is just O of 1. So that's how you solve this problem. And please let me know if you have any particular request for me to solve, or any particular problem that you want me to solve, and I will see you tomorrow with some new algorithmic problem that we are going to solve. And thank you, and have a wonderful day, and I will see you